Hi, this is Dr. Sweeney. This is going to be a review for our Exam 3 review. This one is on hypothesis testing and key important terms for hypothesis testing. It's important that you've already done some work with hypothesis testing before beginning this. It might seem a little foreign or difficult to understand otherwise. Um, Not that you can't use it. It's certainly designed to do that. But what I'd like to do, though, is to kind of like give you an overview, kind of put out the important things and see if we can bring things together to help you better understand hypothesis testing. Okay? So make sure that you have at least have read the section and that you've done some of the homework. I would also recommend doing some of that written assignment on hypothesis testing. Okay, so let's begin. The first thing we want to go with is something called the null hypothesis. The null hypothesis, and it's represented by this thing called H naught. That's how we write it. And the null hypothesis is crucial to doing hypothesis tests because it is the claim that we are trying to reject. So the whole point of hypothesis testing is to reject or fail to reject the null hypothesis. The null hypothesis is what science believes. The null hypothesis is always a parameter and is equal to a certain value in single sample tests. So the way we'll see it is either we're going to have, for a test for means, we'll have mu equals something, okay? Or alternatively, in a test for proportions, we'll have p equals something. And that's because mu is the parameter for the mean, and p is the parameter for proportion. The null hypothesis then gets used in hypothesis testing as the mean of a distribution. So I'm going to use, just for the sake of demonstration, I'm going to use the normal, although the t kind of looks similar. In this case, either I'm going to have mu at the center, or I'll have p at the center. Either one. Mu or p at the center. And because what we're going to do is we're going to determine whether or not our evidence will be rare in comparison to mu or p. Okay, so when we construct a test statistic, what you're going to see is that you're going to get a p or a mu inside of the test statistic. In those instances, that p and mu is the null hypothesis. Okay? The null hypothesis is also the value that we're going to subtract from the sample mean to get our test statistic. So that's what I just said. Okay? Now the alternative hypothesis is a response to the null hypothesis. The alternative hypothesis is what we believe and is either greater than, less than, or different from the alternative. Excuse me, different from the null. Okay? So, how we'll write this in the case of means is we'll get HA will either be mu is less than a value, mu is greater than a value, mu is not equal to a value. And in the case of proportions, we'll be using p is less than a value, p is greater than a value, or p is not equal to a value. Okay? Now, depending upon which one of these that we have for alternative, it's going to determine the tails of our test. And so what that is, it's going to end up becoming really important. It means where is our critical region? And we'll talk about critical region in just a moment. So if we have, and for the sake of discussion, we'll use mu less than, then our tail is on the left-hand side. So that's a left-tailed test. If, on the other hand, we have mu is greater than, then we have a right-tailed test because it's on the greater than side. And if we have mu does not equal our null hypothesis, then we have it two-sided. So that alternative hypothesis comes in really important when we determine the tail of the test, because it's going to tell us where we're going to reject our null hypothesis. Do we do it on the left-hand side, the right-hand side, or do we have to test both sides? Now, rejecting the null hypothesis. This is really important because the whole purpose of hypothesis testing is to reject the null hypothesis. That's what we're trying to do. It's our yes or no. Do we believe the null hypothesis or do we not believe the null hypothesis? That's basically it. Okay, so everything that we do past this point is going to be whether or not we're going to reject or fail to reject the null hypothesis. Okay, what this means is that the evidence that we have for the null hypothesis is not correct. In hypothesis testing, we do not try and prove different values for the claim. It is only to reject or fail to reject the null hypothesis. So that's really important. That's all we're trying to do. Now, it'll tell us things about whether or not it's less than or greater than, but it won't tell us an actual value for the parameter other than it's not the null hypothesis. All right, next, the significance level. The significance level is the probability of committing a type 1 error. We have a name for it. We're going to call it alpha. That's our significance level. The significance level determines for us the size of the critical region. So now, when I look at my distribution, okay, and I've selected that I have a tail, say for example it's mu, okay, is greater than some value for the parameter, and I'm told that alpha equals 0.05, the size of that region is 0.05. That's how big this region is. Okay, the probability of getting some value in there, call it an x, right, in this region, greater than whatever the value is that we have there, okay, is equal to alpha, or in this case, 0.05. Okay, so that's what alpha is. It's the size of the critical region. The critical region is the area that will help us to determine if we're going to reject or fail to reject the null hypothesis. So just as a little foreshadowing, if our test statistics in there, right, in the critical region, then we're going to reject. Okay, so you can understand that knowing how big that region is tells us how likely it is that we're going to reject the null hypothesis. Okay, so in this case, we have a 0.05 chance of rejecting the null. By accident, actually. So a fairly low chance that we're actually going to reject the null by accident. Okay, so just as a review, the significance level tells us the size of the critical region, and it's the critical region that's going to help us determine whether or not we reject or fail to reject the null hypothesis. If we're running a two-tailed test, so suppose that we have mu does not equal some value, okay, and we have alpha, in this case, let's take alpha equal to 0.05. Then what we're going to do is we're going to split it up. So this is 0.025, and this is 0.025. We're actually going to split it in half. So the probability of rejecting when we shouldn't is going to be exactly the same, but, right, we're going to have to account for both sides, all right? So in essence, what happens when we have a two-tailed test is it's going to be harder to reject the null hypothesis. All right. We'll also use the significance level to determine the critical value for the test by finding the z-score or t-score that separate the critical region from the rest of the distribution. The significance level is also what we use to compare our p-value. This is crucial. If p is less than the significance level, alpha, we reject the null hypothesis. You're going to hear me say that a lot. So if our p-value is less than the significance level, we reject the null hypothesis. All right, t-score or z-score. So this is just a reminder that a z-score or a t-score represents the number of standard deviations a sample statistic is away from the mean. The bigger in absolute value the z-score is, the farther it is from the mean, and then the rarer it is. Okay, so like we have unusual values that are more than 2 standard deviations away. So sample statistics that have high z-scores are considered more unlikely. All right, so now what is a test statistic? This is really important when we're doing something called the critical value method. So let's actually put that in here. The critical value method is one way of determining whether or not we should reject the null hypothesis. We have a second way that we'll talk about as well, which is called the p-value method. They are both valid. They both come up with the same result. Okay, so let's look at the critical value method. For the critical value method, we first come up with something called the test statistic. The test statistic is the z or t score that we use to determine the rarity of the sample statistic compared to the null hypothesis. So the bigger the test statistic in absolute value, the more likely it is that we're going to reject the null hypothesis. So let's say, for example, we're going to run a proportions test. My test statistic is going to be p, is going to be z, so it'll be coming from a normal distribution. It'll be p hat minus p. So this is our sample proportion. That's the thing that we've collected, our data from the sample. This p is the null hypothesis. And then we'll divide it by that standard error that we got when we did sampling distributions. So again, p is our null hypothesis. It is not p hat. It's going to be p. P is a null hypothesis. Okay, and it is yes, and it's the population proportion. It's the thing that goes in the middle. Our z-score will have a z. This one's going to be for means. It's going to be x bar, our sample mean, minus mu, which is our null hypothesis, divided by sigma over the square root of n. Notice that sigma is the population standard deviation, and n, if you just recall, is our sample size. And finally, a t-score, t, very similarly to z, is going to be x bar minus mu. So again, our sample mean, our null hypothesis for mu, divided by now s over the square root of n, and this is my sample standard deviation. Okay. So there we go. When we set up our test statistic, this is the comparison that we're going to be making between our sample of data and our null hypothesis. That is that we take the sample data and we subtract it from the null hypothesis to tell us how far, and then we're going to standardize it using that standard error. Okay, and so that's the test statistic. It's going to be very crucial. It plays a big role in the critical value method and also in the p-value method. Now the critical value is the z-score or t-score that separates the critical region from the rest of the distribution. If the test statistic is past the critical value, then we will reject the null hypothesis. The critical value is found by determining the z-score or t-score that determines the size of the critical region. Okay, so if we're looking for the probability that z or t is less than whatever our critical value is going to equal alpha. Okay, so in that case, which is a left tail test, right? Here's the size of alpha. Here's our critical value, which we call T alpha. Okay, so it's going to be the cutoff. It is the line that separates the critical region from the rest of the distribution. Then, if I have a right tail test, here's T alpha, and here's alpha. So we have alpha as the critical region, and T alpha is the line that separates the critical region from the rest of the distribution. And then if we have a two-tailed test, okay, so this was mu less than, here's mu greater than, here's mu not equal to, okay? All right, then I have actually T alpha over 2 because I've got to, in fact, split alpha into pieces. So there's my critical value there. By the way, this could also be called Z alpha if we're using a Z score instead of a T score. Notice up here, when I find the critical value for a two-tailed test, so this is for the two-tailed test, that what I'm doing is I'm going to take the probability that our Z or T is between two critical values, right? Because what I'm trying to do is I'm trying to find two scores, and it'll be 1 minus alpha because it's actually the size of this region right in here. Okay? for the purposes of our exam 3, you're not actually going to be finding a t-score. I'll be giving you a t-score, but it's important that you know what it is, that it is this cutoff line, okay? And that you have an understanding of where it lies inside of the distribution. Okay, now, the p-value, now we're going to get into the p-value method, okay? The p-value method, the p-value is the probability that we will get a sample value, either mean or proportion, that is more rare than the one that we collected, given that the null hypothesis is correct. So, for example, suppose that I have a test statistic called t, okay, and we'll let t be some value. We'll call it t equals b, t equals a. So that's some value there, okay? So we find the t value, here's a, it has a t value of t, okay? And suppose that my null hypothesis is mu is greater than, right, a certain value, the p-value is the size of that region, right? P-value is the size of that region, okay? It tells me, right, okay, what it's going to do is it's going to tell me whether or not the value that I got for, not a, alpha, the value that I got for a is more rare than my critical value, okay? So let me state that again. It's this thing. The p-value is the probability that we will get a sample value, either a mean or a proportion, that is more rare than the one that we collected, given that the null hypothesis is correct, okay? So a small p-value, right, a small region, say for example we have this one, okay, we're going to let mu be less than some value, okay, whatever our null hypothesis is. Yeah. And we have that t is equal to a b, b is a small value. This would be my p-value, okay? What we're going to do is we're going to compare that to the significance level, and I'll demonstrate that in later videos. We'll compare it to the significance level, and if the p-value, the size of the region that we get for the p-value, okay, is in fact less than the size of the critical region, then what we have is rejecting the null hypothesis. So that's very important. To reject the null hypothesis, we're going to compare p to alpha. If p is less than alpha, we reject the null hypothesis. If p is not less than alpha, we fail to reject the null hypothesis. Okay? So, let's talk about rejecting the null hypothesis again, just so that you can get the whole point of hypothesis testing is to determine whether or not we're going to reject or fail to reject the null hypothesis. So in the p-value method, if p is less than alpha, we reject the null hypothesis. In the critical value method, if the test statistic is in the critical region, then we reject the null hypothesis. Okay? Both of these are equally valid ways of going about doing hypothesis testing. You need to know both of them. You need to understand both of them for the purposes of our exam and for the purpose of the final exam. Okay? The p-value method is that comparison between p and alpha. The critical value method is determining if the test statistic is in the critical region, and it essentially comes down to comparing your test statistic to your critical value. Okay? All right, some important notes. One, some important notes about errors. One, a type 1 error, this is when we reject the null hypothesis when the null hypothesis is true. The significance level is the probability of committing a type 1 error. So you may have, this sometimes can be a little bit difficult. You may have some problems with it. If you do, please send me a note. Let me know as you're working through some of the problems in, I think it's 9.3, or it's the third part of chapter 9. A type 2 error is when we fail to reject the null hypothesis when the null hypothesis is in fact false. Okay? Remember that the type 1 error, its probability is called alpha, right? This is the one we want to avoid at all costs, is the type 1 error. Okay? And then the second note that I have for you is also very important, and that is that we use the t-test rather than the z-test when we do not have the population standard deviation for the distribution of the variable. Okay, so these two things, they're actually important notes. This one here we're going to talk more about as I go into some of the demonstrations of both the critical value method and the p-value method. Okay, thank you. This completes our review. This completes the review of key terms and important ideas for hypothesis testing.